Good afternoon. Welcome to the course Thermodynamics of Materials, lectures 93 and 94. We will today continue with the discussion of this. That is, let me write once more. I wrote this last day. That is, this is actually what. Let me remove this part. Let me remove this part. This part. Okay. Wait a minute. So this is actually the 4 issues which make the subject of thermodynamics difficult for students. This we have already completed one, the first one, and today we'll take up the second one. Okay, third one, time permitting. Bapu, Bappa, hello. Sorry for the interruption. 4 issues. Let me write this. Course. We'll take up solution thermodynamics after we complete these 4 issues. These four issues that we are discussing, 4 issues that make thermodynamics a difficult that is, it is better I write that, a difficult subject difficult subject for the students. I have named the 4 issues. First, already discussed, is what? Use of D. Use of the differential operator. It is already discussed last class. Today we will take up the second one. Second one is what? That is concept of reversible, or say simply reversible process. Reversible process, the second one. And third one and fourth one you may recall. Third one and fourth one is what? That I am not writing, okay? As I have already written, so that is actually this presence of constraints in thermodynamic equations or expressions, okay, relations, and presence of constants in thermodynamic relations, and fourth is concept of equilibrium. So this is already done, already done. So today we'll take up reversible process. First, let me give you the definition of reversible process. What is this? It is a process which passes through which is driven by the process which is driven by a finite driving force. I'm very sorry. A process which is driven by an infinitesimally small driving force, making the system move through a continuum of equilibrium states. This is the definition. So let me actually, it is better I should write them here. The process, this is a process, this is a process which is driven by an infinitesimally small driving force, infinitesimally, infinitesimally small driving force. Small means that is, it actually tends to zero. That you read in your calculus, limit h tends to 0. The same concept. Infinitesimally small means tending to 0 driving force, but not 0. No. Then there is no process. I'll explain this. But tends to 0. Limit h tends to 0, dy dx definition. Limit h tends to 0, fx plus h minus fx divided by h. This h tends to 0 but never 0. Anyway, so driving force making the system move through a continuum of equilibrium states. Of equilibrium states. Equilibrium in short, I'll write here, I'm showing you EQ equilibrium in short. I'll write later on, and subsequently, okay. This for the timing I'm writing here, equilibrium, okay, equilibrium states. So often I will write equilibrium, so it will be short form will be better or will convenient. So continuum of equilibrium states. This process may be called an equilibrium process. Equilibrium process, okay. This process may be called an equilibrium process. Equilibrium process. This process may be called an equilibrium process. But the phrase equilibrium process is an oxymoron. Is an oxymoron. Oxymoron, it is a figure of speech. Example of an oxymoron, this side. Achha, this is actually I am removing. Oxymoron. Example for oxymoron is what? Kind cruelty. Kind cruelty. Contradictory ideas are together. Or say deafening silence. Deafening silence, representing silence, and you may say organized chaos, etc. This is examples of oxymoron. So this is equilibrium process. Why oxymoron? Equilibrium means the end of process. Or process means which is in a non-equilibrium state. So let us actually the term equilibrium means the term equilibrium means okay. The term equilibrium means okay, means what? Means the end of a process. End means the end of a process, and that and the term process and the term process means and the term process means a lack of equilibrium. This apparent contradiction, this apparent contradiction this apparent contradiction confuses most students. Confuses most students. Most students. Okay. It should be noted that a reversible process is impracticable. A reversible process is impracticable. Achha, I am writing this side. I use this side. Impracticable. Impracticable. Let me remove this. These are actually used already. Is impracticable in as much as uh, we carry out in as much as it is to be executed by an infinitesimally it is to by an infinitesimally small driving force. It is in as much as it is to be by an infinitesimally small driving force. Small, how much it is? Tends to 0. Driving force. We carry, so how do we carry out? We carry it out. We carry out inside. We carry it out. How do we carry out? Then inside our head. Inside our head. means it's a mental process. So thought process will actually execute reversible process. We carry it out inside our head. Then even so, even so, the importance of the reversible, even so, the importance of the reversible process is immense. Is immense in the study of thermodynamics. In the study of thermodynamics. In future or subsequently, thermodynamics will be shortened as thermo. We will use thermo. So we will understand short form. So thermodynamics. Let us now go through. Let us now go through this. Let us now go through the following. The following question and answer. Question and answer. Question and answer discussion to understand discussion to understand and clarify to understand and clarify major doubts faced by major doubts faced by students. So we'll take up question answer session. So first question is say A. What is the question that we face? Why should we study the reversible process? Then why should we study? If reversible process is impracticable, then why should we study this? Let us see, why should we study the reversible process? The reversible process. Reversible in short, I'll write reversible. Short form, reversible. Okay, let me write here. Write here some. Equilibrium, short is equilibrium. Thermodynamics, right? Short form, short. Thermodynamics, dynamics, short, maybe thermo. And now what it is coming? Reversible and irreversible. Reversible, short is reversible. Irreversible, short, irreversible. Reaction, short, reaction. You follow this shortened form, then actually it will save time. Okay, and it is, you will easily understand this. Why should we study the reversible process at all when we know we know this when we know this process is impracticable. Impracticable. This is the question. Why should we study the reversible process at all? When we know this process is impracticable. Answer. So this is the first one. Question. Answer. Let us take up the answer for this. The reversible process the reversible process the reversible process reversible process the reversible process offers a standard offers a standard or reference for the or reference standard or reference for the irreversible processes, the benchmark, standard reference. So for the corresponding irreversible process. For example, reversible isothermal expansion, irreversible isothermal expansion, reversible adiabatic, irreversible adiabatic, or reversible constant pressure process, irreversible constant pressure process. So this is okay. This is the one. So what is this? For example, let us continue with this. For example, let us explain. For example, to in order to cause greater and greater greater and greater and greater work done by the system work done by the system work done by the system on implied on surrounding on surrounding on the surrounding the on the surrounding. Here also another one. So here surrounding short form surrounding, just SURR surroundings in short. So okay, on the surroundings. Okay. For example, given by the system, sorry, in an irreversible process, in an irreversible process, the process should get the process should get closer and closer, get closer and closer, closer and closer to the respectable, to the reversible standard, to the reversible standard. Reversible standard. Okay, I'll continue with this here from this irreversible standard. Okay, so for example, we can carry out an irreversible isothermal expansion. I start this point here. It is better I go off here. So I remove all this. Reversible process we continue. Reversible process we are discussing. I remove all this. So just mention that the item 2, which is reversible process. The 4 issue, second issue, reversible process under discussion. Just keep it on the top as the subheading. Okay, this. Okay, so we can start. We can carry out. We can carry out. What is this? We can carry out an irreversible isothermal expansion and irreversible isothermal expansion, irreversible isothermal expansion process between an initial state we may call it P1 V1 T, between an initial state and final state, and a final state. What is that? P2 P2 V2 T, P2 V2 T. Where you note this, since the expansion, what does it mean? P2 must be less than P1, that is understood. By carrying it out, so what is our aim? To get closer and closer to the reversible. Let us see how. By carrying it out, this is an irreversible process we have considered, but we try to make it go closer and closer to reversible, which is driven by infinitesimally small driving force. But I missed one point. What is this? Irreversible process. Where I wrote. Here for the corresponding irreversible process, here you write standard irreversible process is driven by finite driving force. Okay, driven by, just here add this, driven by a finite a finite driving force. Okay, I missed this point here. Irreversible process is what? Which is driven by finite driving force, compared to reversible process, infinitesimally small driving force. This is a finite driving force. So, which one? The irreversible process, which is driving, which is driven by, you can write in bracket this, irreversible process, which is driven by, this I actually taught you when I discussed reversible process and irreversible process, okay, in the introduction. But okay, I have to repeat this because I want to explain the issue, the difficulty of understanding reversible process. Okay, this discussion will be different from what I discussed previously, but anyway, that concept must be there, and that concept will be used here. So please follow this. By carrying it out, by carrying it out, as I told you, by yeah, carrying it out in number of yeah, in multiple steps. Multiple steps like e.g. e.g. So e.g. what? Not directly P1 to P2, but P1 to P3, an intermediate value, then to P2. Multiple. It can be further reduced, like say more number of steps, like say between P1 and P3, P4, P3, P2, P5, etc., etc. So I am giving simple example: P1 to P3 to P2, where P1 is greater than P3 and still greater, and P3 is in turn greater than P2, rather than rather than rather than in a single step. In a single step, what is that? P1 directly to P2. This is irreversible. This is irreversible. Reversible is just extreme, ideal. In infinitesimally small driving force. For example, what is the driving force here in this part? P3 minus P1. What is the driving force for here? For this step, P2 minus P3. Remember, I am very sorry. Here it is. What is the driving force? P1. This difference. P1 is greater. P1 higher pressure to lower pressure expansion. P1 to P3, P1 minus P3 is the driving force for this step, and here P3 minus P2, and rather than in a single step, so P1 minus P2, where the driving force is what? Delta driving force given by, you understand this, here I am writing driving force given by P1 is greater minus P2, which we call delta P, delta P. This is for, so we will, very interesting this. So we will actually carry out, since if we will not be able to carry it out in reversible way. So as much close to reversible process as possible, as close to the reversible process as possible, that we will try. Or so it's examples, just reduce the driving force, if not infinitesimally small, but reduce the driving force and number of steps, okay, and that is actually, this is the happening. So this the more important is, or rather similarly, I'm very sorry, similarly compression I will consider now. Similarly, in a irreversible compression process, okay, similarly in an irreversible, similarly in an irreversible isothermal compression, isothermal compression, in isothermal compression process between 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 the initial state P1 V1 T to the final state P2 V2 T. Acha, I mentioned, I forgotten to mention on the system. I forgotten actually. That is actually what is the system. I have forgotten the expansion of an ideal gas. Achha, here we can carry out an irreversible isothermal expansion process of an ideal gas of say 1 mole of an ideal gas, ideal gas. This is a system I should specify. Process is this isothermal irreversible expansion. System 1 mole simplest ideal gas. So similarly, an irreversible isothermal compression process. Process with, I am very sorry, off. Process off now. Process with 1 mole of an ideal gas as the system. As a system, I can write between. Yeah. So similarly, in an irreversible isothermal compression process, with between sorry between the initial state between actually, sorry, time is short, between the initial state process with, right here, with 1 mole ideal gas. We should be clear about our objective. So that is, say, okay, very good. This is a compression to the final state. How we will carry out irreversibly? We know P1 to P2 directly, but we want to get closer to the reversible counterpart. So what is this? The process should. So yes, right here, what is, since it is a compression, note this, it is P2 will be greater than P1. Since compression, that is sure, P2 greater than P1. In order to in order to in order to in order to cause in order to cause in order to cause less and less this time work done on the system. This is compression, less and less work done on the system by, obviously implied by, surrounding. A compressor, as an example, compressor. So by surrounding, sorry, by surrounding, the process should. Let us see, read the sentence. Similarly, in an irreversible isothermal compression process between the initial state, etc., in order to cause less and less work done on the system, what we should do? The process should get closer and closer to closer and closer to what is this? Closer and closer to the reversible process. To the reversible process. To the reversible process by carrying it out. By carrying, is like the expansion discussion. By carrying it out in multiple steps rather than in single step. Okay, multiple step irreversible, but multiple steps. Okay, so that it gets closer to the irreversible. I am very sorry. It should get closer to the reversible compression. So please follow this. Closer and closer by carrying out a multiple step. E.g., for example, P1, the higher pressure, okay, what is lower pressure to higher pressure. So P1 goes to P3 like before, which get us P1 to P3, get us P3 to P2, is still greater. So that is, you can write P1 lower compression means lower pressure to higher pressure and work done on the system by the surroundings. Okay, you want to be the rather than P1 to P2 rather than in a single step. Let me write this correctly. In a single step, what is that? P1 to P2. So like this, okay. So I can show you the figure in case. I can show you a figure here. Just consider the first one, expansion. Expansion figure. So recall this reversible expansion. Follow this. Easy diagram. P versus V and isothermal. Reversible isothermal expansion. You know, this is the expression volume increases. So what is the state 1? State 2. Halu right here. Describing P1, V1, T isothermal, P2, V2, T. What I said, this is reversible, right? This is unique, reversible. So that's why it is actually solid line, no dotted. But if it is irreversible, is what? Infinite number of irreversible. Just for example, the straight easiest is what? Simplest, easiest, commonest is what? Straight P1 down to P2. Sorry. Recall this. This is I am giving double arrow to show irreversible. So P1 to P2 directly. This one. So why we recommend this? Because this is work done by the system is greater in the reversible than the irreversible. Work done by the system is area under the curve. Now, what is recommended here? Try if you cannot perform a reversible process, try to get closer to the reversible, or try to get closer to reversible process. So if I want to get closer, what shall I do? I will consider another intermediate pressure P3. So P1 drop to P3. This actually happens no. Sorry. What happens? Then from here it is actually what pressure it is? It is P3. P1 to P3, drop, and here it is equilibrium again, P3. Then, but the destination is P2. So again, drop, P2. Now you will see what happens. Area under this curve is greater than this curve. What is the area here? This is clearly see, okay. So I'm not giving this. So area under this irreversible is this. What is the area? This area under the curve. But this will provide a greater area. This one, okay. If we get this, and greatest area is what? Reversible one. So try to close up to the reversible process as much as possible. So like this. So these steps. This is the expansion. Expansion I discussed. Compression the opposite. Compression will be what? Compression. It is okay. These are dotted. Remember, because since it is irreversible, dotted only this point is equilibrium state. Okay. Don't worry. Compression. Wait a bit. I hope this will be okay. So this is the one that I wanted to mean here. P1 to P3, then P3 to P2. Now this is what is the good thing about it. Is this the area under the work done by the system is greater here than which one? Than 1 to 2 greater. Greatest is what? The reversible one. Area under the curve is greatest, and we know analytically we can show this. So this is the okay. And compression, quickly do this. Compression opposite. Compression again draw. This is the PV diagram. Sorry, PV diagram. Here also again draw PV diagram quickly. Quickly you have understood by this time, I guess, what is the why. So this sets a goal. Reversible sets a goal. Idea for the irreversible processes. So because this is related to maximum work done by the system or greatest work done by the system. So again compression. So this time you have to consider this isothermal 1 to 2. One is what? P1 V1T compressed to P2 V2T. You clearly see here what you see here, volume is decreased. Okay, so P2 is greater than P1 here, right? And here P2 is less than P1. You will note this. Okay, this is already written here. Quickly, this is a reversible. Sorry. This is the reversible right here. This is the right here reversible compression. What is the irreversible compression? Easy, simplest is what? 1 and you directly go up to 1 to 2. So dotted line 1 to 2. Irreversible. But we'll try to we will try to adapt irreversible process with multiple steps for smaller driving force. How? So we will not go all this way. We will do this thing. P1, suppose this is the P3, say again like last time, P3. So we will go dotted, still dotted, and go dotted to P3. Then again P3 to P2, P1 to P3, P1 to P3, P3 to P2. What gain you will get from this? What gain? Okay. So this is actually, see, I can give double arrow for reversible, etc. But anyway, then what we will get from here? The work done this time, this is work done on the system will be minimum here in case of reversible. Okay, work done on the system is minimum. Okay, because this work done is actually, if you follow this, this is actually this is a this is actually compression work, so negative. So this area is maximum, means negative maximum means minimum work here, and here it is greater than that. So but if we take this multiple step approach, then this will be smaller than this. This will be, the magnitude will be smaller than this. Okay, so this is actually, this is suppose this is suppose minus 40, and this is say minus 30. So this is actually work done will be less. Work done by the on the system will be less here. So minus 40 is less than minus 30, and this will be somewhere between minus 35 to minus 35. So this will be closer to reversible process, and this work done is actually minus 35, which is even smaller than minus 40. So work done on the system will be less, and we need that. Because work done on the system, the compressor has to do less work on the compressor is the surrounding. Gas is the system, has to do less work. So anyway, this is how actually this is happening. This is okay, very good. Very good. Here volume, remember here volume decreases, here volume increases. Okay. Careful about this. This is actually wanted to give the skates. So continue with our discussion. So this part is over. The first question is, can I remove this? Yes, I am removing this. Okay. Remove this, and I am taking up the next question. First question we have answered. P1 to P2. Next is acha. Now this is not all, but more importantly, here little bit addition. More importantly, this part is over. As we have discussed, that we should get closer and closer to the reversible process to have greater work done by the system and less work done on the system. This is the principle. Okay, because in reversible process gives the maximum work done by the system and least work done on the system. So more importantly, more importantly, were it not for the reversible process, were it not for the reversible process, we would not get the classical definition of entropy. What is the definition? You know, ds is del q or dq, call it reversible, dq reversible by t. T means it is T system. I am writing this in case you have no doubt what is T system. So this definition relates with the reversible process only. And if you consider this, okay, fine. So this is, and the second law would not be followed. And that's, if entropy were not there, the second law of thermodynamics would not be formulated. And the second law of thermodynamics and the second law of thermodynamics, thermo would not be formulated. Thermo would not be formulated. Will not be formulated. Will not be formulated. The connection between, you might ask, what would happen if we consider dq irreversible process that we can execute? Let us see the connection between ds and dq irreversible which we can carry out, then which is practicable, which we can carry out. So the connection between this is what? ds only greater than, ds greater than dq irreversible by t, that is dq irreversible by t system, So this is, if it is greater than, does it give any definite value for ds? So what is this? Which means an irreversible heat interaction means dq irreversible heat interaction cannot or could not rather could not definitely give the value of ds, could not definitely give the value of value of ds. Oh, sorry. With this, question 1 is over. Question 1 was what? Recall this. Why should we study the reversible process at all when we know that it is impracticable? Answers over. So we'll take up the next question on reversible process. Topic is remaining this reversible process. Continue. This is the first example we took. Then we'll take up two more examples, 2 or 3 maybe. Let us see. So this is actually, see what I said here, that this value says that it is that ds is greater than that. Greater than how much greater? We don't know. Greater only. So it is not definite value of ds. So this is, with this actually we quit this first question and with question answer discussion for the first point on reversible process issue. So we'll take up the next one. Next issue. Start here. Next issue is what? Next question. Again question B. This is question A over. Next question is what? Question is confusion of the students. Confusion from the students. So the second law criterion. The second law criterion for equilibrium or reversible process, equilibrium or reversible process is what? You know, dg pt is 0. This is, we say, I have discussed on this equilibrium. The first issue was equilibrium. I am sorry, D. I am very sorry, D. Use of D. So I have discussed this for equilibrium. Now reversible process I will discuss today, since the topic is reversible process. How we are applying this for reversible process? So what is the question? How can a question is this? How can a reversible process or reaction? So a reaction can be carried out satisfying what? Satisfying dgpt is this one. dgpt is the answer. Let us discuss this. Okay, this will take some time though, but we should clarify our confusions and doubts. Let us get answers for this answer. So let us consider the reversible evaporation of H2 liquid into H2O vapor. That is phase transformation. So I am writing this as H2O liquid goes to H2O vapor. Call it equation 1. Remember, this is a reaction, chemical reaction. Phase transformation is a kind of chemical reaction because they are governed by the same second law. The delta G is 0 for equilibrium, delta G is negative for spontaneity, and delta G positive for impossibility. So same actually, only outwardly both sides this H2O, same species for phase transformation, only phases are different. And there we have actually say M plus O2 is MO2, but principle is same. So we actually consider this as a chemical reaction also. So let us move on. We must understand that have to little bit explain this. We must understand. This is the goal. This is the goal. We will carry out reversibly, and we will show that this satisfied. This will show. We must understand that the term reversible, the term reversible, reversible and the term reversible and equilibrium are essentially synonymous. Essentially synonymous. Only the term reversible applies to a process, and the term equilibrium applies to a state, refers to a process, and term equilibrium applies to a state. Equilibrium state we say, reversible process we say. So these are the things that actually refers to a process. So in order to carry out a reversible process, so in order to carry out a reversible process, so what we shall do, the whole process will be under equilibrium. So a system must initially be at equilibrium, must initially be at equilibrium. This is the starting state, it should be equilibrium. Then you carry out, if you want to carry out a reversible process, start point is full equilibrium, then make it reversible, and very infinitesimally small change, then you have a reversible process going on. Okay, so be at equilibrium. So and this the condition is this initially at equilibrium, and the condition for equilibrium is and equilibrium and the condition for equilibrium and the condition for equilibrium is delta G is 0. That gives you that is GH2O vapor minus GH2O liquid is 0. That is GH2O vapor is GH2O liquid. Call this equation 2. 1 here, 2. Okay, this is this. Let us consider now next. Let us consider a finite quantity of water, liquid water, finite quantity of water liquid kept in equilibrium with that. No, it's okay. Let us consider a finite quantity of H2 kept in equilibrium with what? A finite quantity of water vapor. Finite quantity kept with a finite quantity of H2O vapor. Finite quantity of H2O vapor in a system with cylinder piston arrangement. Cylinder piston arrangement with a cylinder piston arrangement at a in a system with cylinder piston arrangement at temperature T and pressure P. At temperature T and pressure P. T and pressure P. For example, when T is 342 K, pressure is nothing but the saturated vapor pressure of water, which is nothing but at this temperature 0.3 atmosphere can be obtained from the okay from this section is obtained from the equilibrium constant of equation 1. Obtained from the equilibrium constant of this reaction 1 or equilibrium 1. Okay, equilibrium constant of equation 1, okay, or reaction 1, okay, or equation 1. Okay, this is okay, this is fine. So this is okay. So let us consider finite quantity of H2O liquid kept in equilibrium with a finite quantity of H2O vapor in a system with cylinder piston arrangement at temperature and pressure initially. Initially we add this because we are going to change something. So initial state must be fully defined. So we have defined this. I will give you a sketch here. I will give you a sketch shortly. Okay, this is the okay, very good. At this state, this is given in figure 1. Figure 1A. Sorry, figure 1A. At this state, no process may occur. No process may occur. Okay, reversible or irreversible. Reversible or irreversible. Oh, irreversible. Oh, sorry. Irreversible, reversible, reversible or irreversible. Irreversible. Reversible or irreversible. Okay, since I've written here, let me write this full. Reversible or irreversible. Cannot? Okay. Because this is a, because this is a perfect equilibrium state. Perfect equilibrium state. Because we are kept, it is not reversible process yet. The perfect equilibrium state. This is the perfect equilibrium state. Note, note a reversible process. How it is different from reversible? Note a reversible. I am repeatedly saying this. Note a reversible process. Note a reversible process occurs under a condition. Occurs under a condition infinitesimally, which is infinitesimally displaced. Infinitesimally, infinitesimally mainly displaced from the equilibrium state, from the equilibrium condition. So this I will show in figure 1 soon. Okay. So let me write this first. Okay. Let me explain this. So figure 1. Okay. So if we right this, if you intend to now, okay, reversible is reversible. Okay. Okay. Very good. Reversible is reversible because this. If we intend to, I I I I just keep the question only. I remove all these things. So give a star here. Give a star. Star here. And remove this. Right here. Right. Let us write this out. Okay. If we intend to star, if we if we intend to if we intend to vaporize dn moles of vaporize dn moles of dn mole rather of H2O liquid into dn mole of H2O vapor, H2O vapor, okay, vapor, H2O vapor, reversibly, 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 the external pressure, the external pressure must be what? Inside is P, must be P minus dP, must be infinitesimally changed to infinitesimally change to T minus dP. T minus dP, that is, as I have taken example here, what is this? 0.3 atmosphere, say. That is, if I use this data, 0.3 atmosphere and temperature is 342, then it will be more realistic. That is 0.3 minus dP to P minus dP, while keeping the temperature constant at T fixed at 342, keeping T temperature T fixed at 342 Kelvin. So only a change is here. We are doing this. Okay, at 342 Kelvin. Okay, this is figure 1B. Figure 1B. This is figure 1. Oh. Figure 1B. So I will now sketch this, remove all these things. Just I'll give you the figure. Okay, let us draw the figure 1A and 1B. That will help you. Start. This is your initial state. What I have kept here, this water, liquid, water liquid, as you see here, water liquid. And here you have these are water vapor, and this is the pressure, external pressure. So what is this? H2O liquid, means pure. Not to mention this is H2O vapor. What is the pressure? Saturated vapor pressure, pH2O 0 is what? It is this pH2O vapor. pH is 0.3 atmosphere. But this is for what temperature? 342 K. So let us thermostat this arrangement. Thermostat, surroundings, actually surroundings. So this is thermostat. T is what temperature is maintained? 342 Kelvin, which is okay. And what is this pressure? Since it is equilibrium state, it is exactly this external pressure. This is surrounding, this is surrounding. P is, you know this, P is what? Exactly balance. Then what it is this? This is called this actually initial state. Initial state, and you know very well, this is your starting point and this is the equilibrium state. The equilibrium state. This is not reversible process yet. It is perfect, right here, perfect equilibrium. Perfect equilibrium state, right? Perfect, right here, perfect equilibrium. This pen is not behaving well. Perfect equilibrium. Now we actually see this is figure 1A. Okay, good, very good. Figure 1A. What else? Anything else here? I missed this? No, I don't think I missed anything. So next is what? You consider this reversible process. You are carrying out a reversible process. So I'll show you. Not only reversible, I will show you irreversible, since with the same figure will be very convenient. Otherwise, I have to This again see again similar thing actually. Wait a bit. Actually, let me rest this for a while so that let me try another one or maybe still another one. Let us see what happens here. Sorry, start here. Okay, similarly, it is too big. Actually, similarly, same type of diagram I should draw. Good, good, good. Again, you have place water, liquid. Happy, and then you have these are the vapors, H2 vapors. You have your piston P. We discuss this again. You give this H2 vapor. What is this? H2 liquid. Again, same thermostat, namely 342 Kelvin thermostat. This will be your figure on. Achha, what is this? This is the write this. This is the achha, what pressure should be H2 vapor. Okay, vapor. This is hot pressure. It was 0.3, but this time it cannot be 0.3. If it is 0.3, it remains there. Equilibrium remains at equilibrium. Reversible process is infinitesimally different from reversible to equilibrium. Reversible process is infinitesimally different from the equilibrium state. How? It cannot be 0.3 to make a to run a process. To make a process reversible, the name, there should be imbalance, driving force. Infinitesimally small, it may be 0.3 minus dp. The inside is here, what value? 0.3. This is 0.3, this is 0.3 minus dp. So there is a pressure imbalance, as a result of which what will happen? This liquid, there will be liquid will be vaporized and put some vapors into this, so that moles, dn moles, perhaps dn moles, then it becomes here, it is 0.2 minus dp, so it is also 0.3 minus dp under this. But when you add some dn moles of vapor going there, then it becomes 0.3. But the moment it is 0.3, but this is sustained, 0.3 minus, like this, sustained, then again imbalance. It is 0.3, but it is 0.3 minus dp sustained, so again imbalance, again vaporization, dn moles, dn moles, dn moles. See, it doesn't stop with dn moles. Dn, any number of delta n, any finite number of moles can be done this. So write this. Sustained is one you have to write, but if you write this is reversible. For reversible, sustained you write sustained you write here. This I'll mention. This is for reversible evaporation. For reversible evaporation. And what right at this place, we are considering reversible process, so this answer is there. So this will process. But in case you are considering irreversible evaporation, if you ask me, then it is finite driving force, so it cannot be dp anymore. Delta p for irreversible evaporation. Remember, dn will for reversible, the finite moles can be not just dn moles. A finite moles can be evaporated. The whole of liquid water liquid, H2O liquid can be evaporated by irreversible process, by reversible process, and also by the irreversible process, no problem. So not just dn moles will be evaporated. Dn moles, then again dn, integration of dn is what? Integration of dn is delta n, a finite value. A finite value means any number of moles, the whole of water of 50% of water, whole of water. So this is okay. Let us give this caption is little bit okay of this. This is actually you have to write the reversible evaporation. Since reversible is the topic, just in passing I have noted this. Just you may note this. This is extra addition. Reversible evaporation. The external is just 0.3 minus dp and or irreversible and irreversible evaporation. This is additional thing here. Irreversible evaporation. The external is 0.3 minus delta p for of any number of for evaporation of evaporation of any number of H2O liquid molecules, for any finite number of H2O liquid moles evaporation. This is shown. This is figure, what you call this, figure 1b. So 1a is perfect equilibrium. This is reversible equilibrium. Under so just forget about irreversible. Reversible equilibrium all the way. dn under equilibrium. Reversible and equilibrium is actually synonymous. So under, because it is under what pressure? 0.3 minus dp is actually point. So let me write a few lines here. That will be helpful. So these figures are giving. So so actually I may write something here. Okay, let us write this out. Okay, that will clarify this. Okay, since right, this figure 3. For this pressure, now start. Here no pressure is perfectly balanced. Imbalance, small though imbalance, pressure imbalance. For this pressure imbalance, what I wrote? Continue from here. Continue from here. Give a star and continue. For made 0.3 minus dp external pressure imbalance from the system. System tends to be 0.3 minus dp. Then the process triggers off. For this pressure imbalance, as I told you, for this pressure imbalance, dn moles of liquid will evaporate. dn moles of liquid H2O, liquid H2O will vaporize to increase the pressure P system back to increase the P system back to what value? See, under this 0.3 minus dp, it will be 0.3 minus dp. As a result of which it adds. Okay, so point is pressure imbalance. So how will you give pressure inside? Is 0.3 minus, we will try to make it 0.3. By why? Because this requirement is 0.3. At this temperature, chemical requirement is 0.3. So add some moles in this volume, get a number of, as the number of mole increases, pressure will increase. So dn moles will actually increase dp pressure. So it will be 0.3 minus dp plus dp back to 0.3. But again, imbalance. Still there. Imbalance is okay, fine, it's balanced and 0.3 is like this. But 0.3 minus dp means again the same set of occurrence continues, that is 0.3 minus dp pressure imbalance. So again vaporization and continues. So P system back to 0.3 atmosphere. Let us see. But this is not enough. 0.3 atmosphere. Since the external pressure Since the external pressure is maintained or sustained, is maintained at is maintained spelling maintained at what is maintained 0.3 minus dp means what I wrote sustain means maintain 0.3 minus maintain at 0.3 minus dp. This will this process will continue this process will continue evaporating integration of dn is delta n, that is a finite number of moles, that is a finite number of moles of H2 integration dn. Oh, integration dn. Finite moles of H2O liquid, finite number of moles of H2O liquid into H2 vapor. Or continue or not. Control evaporating is not. Will continue. Will continue evaporating. Will continue evaporating. Evaporating. It's okay. Evaporating. That is a finite number of moles H2 liquid into H2O vapor. H2O vapor at the temperature of 342 K and what? And pressure is this, at this pressure finite number of moles reversibly. And what is this called? And pressure of what? 0.3 minus 0.3 minus dp, which is nothing but 0.3 itself, 0.3 atmosphere. 0.3 when you dp subtract, integrate dp, you cannot ignore integration of dp. dp tends to 0, you cannot ignore in multiplication or division or integration. Integration dx, dp is delta p, dx is delta x. But when it's subtraction, 0.3 and dp is where? dp is something tends to 0. What is the result? 0.3 is 0.3 itself, okay? But you have to understand that with 0.3 in this situation, equilibrium. No process, no reversible, no irreversible. This is to be reversible, 0.3 minus dp, to be irreversible, 0.3 minus delta p. This. So two things I tell you here, that reversible process, you can, in the reversible evaporation, you can evaporate finite number of moles of liquid water into vapor. Finite, means say 1 mole, 2 moles, 100 moles. dn, you start dn, but dn integration is finite. And irreversible also we know that a finite number of moles can be evaporated. So same number of moles can be evaporated either by reversible process or irreversible process. But they have a essential difference. Driving force is one is 0.3 minus dp, is 0.3 minus delta p. This is actually how we are reversibly evaporating water into vapor. Okay, 0.3, the pressure is 0.3 atmosphere. Okay. Is P is, so I'm writing is the pressure of 0.3 minus dP is 0.3 atmosphere. Okay, so we can conclude. So we can conclude that dn moles, or for that matter delta n. Delta n means any finite quantity. 1 mole, 2 mole, 3 mole, 100 moles, or then delta n. Dn moles is what? Tends to 0, but not 0. Or delta n moles of water liquid can be reversibly. This is important. So this is actually that water evaporation is how reversibly carried out. Can be reversibly can be reversibly evaporated into the same number of moles of into the same number of moles of same number of same 2 moles to 2 moles, 3 moles to 3 moles, dn moles to dn moles, same number of dn moles liquid to dn moles vapor on dn moles, same number of moles of H2O vapor at temperature T and pressure P minus dP is what? P. That is P. At pressure P minus dP, that is P. That is P. That's it. This is actually part of this answer. Answer is not complete yet. This I have to show how it is 0. But this is the reversible evaporation. Discuss this. So fine, very good. Remember, but one thing you should be careful about the PT. PT. This is actually, phase diagram, or say what is this called, single component phase diagram we have completed. These are mutually dependent. So if this temperature is this is 0.3. It cannot be otherwise. If you want to change this pressure, it should be a different temperature. At this temperature, only uniquely this value, or this pressure, this. They are actually mutually they are actually compatible values. This temperature, this is the compatible values, no other. So this part discussed, and now actually take up this question. So the remaining parts, I remove this now. I don't need the figures. Oh, one figure I'll draw though, but that I'll show at the end. Let me finish this first, and let me prove this. Yes, reversible evaporation you have understood. Every day water is evaporating, but how to carry out reversible? Since reversible process, we doubt sometimes whether it is important, it is practical, etc., etc. But you see that reversibly you can evaporate water. Similarly, other examples I will take up, maybe 2 more. But before this, let me finish this part. This part, if I finish, then that will be very satisfying for today. So please continue with this. So continue with this. Now let us take up The original question. The original question. What is this? Na I. This is the original question. How can be reversible process be carried out satisfying DGPT is 0? How is, I am repeating this, question is what? How is DGPT, oh by the way, anytime remember, when you are asked to reversibly carry out, in this case, you say reversibly I carry out at what temperature? 342 Kelvin and 0.3 atmosphere you say, but you full well know that it cannot be exactly 0.3. Then it is equilibrium, no process. Then you know in your okay, you know yourself that it's 0.3, but to be reversible 0.3 minus dp. Otherwise, reversible process will not be executed. And now, then why people say it is 0.3, 342 Kelvin and 0.3? It is implied. 0.3 minus dp is 0.3. But actual process requires a infinitesimally small driving force like 0.3 minus dp, and so that process may occur. So 100% equilibrium, perfect equilibrium should be disturbed. If you don't disturb, then it will remain equilibrium forever. No process will occur. So let us take up the original question. How is DGPT is 0 for in the reversible evaporation carried out? In the reversible evaporation carried out. A moment ago we carried out. How the DGPT is 0? So just now carried out. You understand? Question mark. This question I am repeating here. So let's start. For this consider, now for a little bit mathematical, for this consider, and you are used to this, number of times I am doing this. For this consider, right, G prime is a function of extensively, right, pressure, temperature. Tell me what are the systems? H2O, shall I write anywhere? H2O liquid goes to H2O vapor. This is the reaction. So G prime function of pressure, temperature, and NH2 as we write liquid, NH2 vapor. That you have to write. Remember, this is all are independent, mutually independent. 43, 10 minutes. Okay. H2 liquid is H2 vapor. Just this is actually our evaporation process. Okay, good. This or what you write this, remember, these are all independently. You can consider this. Our system. A system is this, you can consider PT. Okay, or dg prime is what? Tell me quickly. Delta G prime, delta G. Recall. Constant temperature, NH2 liquid, NH2 vapor times dp. Remember, plus tell me del G prime, del T. You know, recall, constant pressure, constant NH2 solid liquid, NH2 vapor. Recall, times dt. Happy? Plus del G prime by dt. What next? Next is what is this? Oh no, sorry. Why? Next is NH2. Del NH2O liquid, sorry, temperature, pressure, and NH2 vapor, and we add here D N H2O liquid, and here last one del G prime del NH2 vapor, NH2 vapor and give this under again constant temperature, pressure, NH2 liquid the other one, and DnH2 vapor. Okay, this is now you recall this, what is the under constant pressure temperature, but before this, what is the name of this? Tell me, recall, what is this derivative? V or V prime, P or V prime. This, since it is a prime, you should write VdP minus SdT. This is VdP minus, this is the D, V prime here, and this is here minus SdT, S prime. Since prime are using minus S prime. So, but under constant pressure temperature, these two terms drops out, these two terms. Pressure, constant temperature. So remains this. This is known as what? Tell me, this is known as partial molar free energy of H2O. This time I am not writing partial because pure liquid, it is actually just molar free energy of H2O. And partial comes when there is a solution or mixture, but it is H2O liquid is pure. So GH2O, and this is also, tell me what is GH2 liquid, please. GH2O vapor, molar, not partial, molar free energy of liquid, molar free energy of vapor. Good boy. So what it is there? Write this out. GH2O liquid, quick, DnH2O liquid plus GH2O vapor, DnH2O vapor. Okay. Now noting, we do one thing here. See stoichiometry. See 1:1. So Dn to Dn. So Dn evaporation means H2O decreases and H2 liquid decreases and H2 vapor increases. So minus, decrease to make it positive minus DnH2 liquid is plus DnH2 vapor, and we name this as plus Dn is positive, or Dn is positive. So what you do this, if you substitute this thing here, what you will get? GH2O vapor minus GH2 liquid, happy, you give a bracket and just Dn instead of this. This is a common name Dn. Okay, here, sorry, just Dn. Dn is positive. So this now from which equations? So recall the equations that actually we have. Give these equations. So here GH2 bar. Oh, I have removed this. No, I have not. Call this equation GH2 Dn. Okay, call this equation 3. And what is equation 2 already there? Recall equation 2. 3. Since, keep it there. Since at Pt that is P minus Tp dt, P minus T dP that you have removed this, the reaction is in equilibrium. Reversible means the reaction H2O liquid is H2O vapor is in equilibrium. In equilibrium means under reversible condition. Okay, is in equilibrium. Is in equilibrium. Reaction H2O is in equilibrium. Pt and P minus dP is actual Pt. This reaction is under reversible condition, means equilibrium. Then what is the condition for reversible and equilibrium? Recall this. What is this? GH2O this is in equilibrium. So GH2 vapor is GH2O liquid. This I already gave you. Recall this was 2 already. Given already. See, under this condition, at Pt or P minus dP free energies are okay. That is, free energies are same because this is the equilibrium condition. And reversible condition is also equilibrium condition. This okay. This is already equation 2. So from 3 and 2. So from 3 already given. This is given already previously. So from 3 and 2, What you get? Tell me. dgpt is dg prime pt is what? This is equal means this is 0, proved 0. So the dgpt is 0. Okay. So how can a reversible process carried out? dgpt. So proved, in a sense proved. You can write this so that it is ends here. Still an answer. If a finite to be 2 hours or to be 150.
152 already has closed.
Okay. If a finite, don't worry. If a finite, okay, I'll take 5 minutes. If a finite number of moles, instead of dn dg, if a finite number delta n, if a finite number of moles delta n, which is nothing but integration of dn, is integration of dn, are thus reversibly carried out. Now we will always consider finally finite changes. dn changes is infinitesimally small. Finally, we want a finite change. That we have seen. Finite reversible process expansion, reversible expansion of isothermal gas, finite changes. State 1 to state 2. Always this. So here also are thus reversibly carried out are thus reversibly carried out at pt. Again I write this. I always write this at pt, but actually to be processed p minus dpt. Remember this. Otherwise it won't be. Okay, but still, okay, that it maintains the equilibrium. Okay, reversible and equilibrium synonymous at p minus t dp. Okay, what is this? Okay, at pt or p minus tp dp, then delta g prime pt would be what? Delta g prime pt will be obtained by means I tell you, when you are reversibly carry out, not only DL, continuously carry out reversibly, then under what pressure? External pressure P minus dP sustained and temperature T. Under this condition it is going on, and inside is always this liquid vapor equilibrium. Liquid vapor equilibrium is existing, is upheld, liquid vapor. But it is going through a finite changes, but all the time this maintained. This is the actual reversible changes. Reversible, however, utilizing the equilibrium, but it is okay. This is this, okay, and okay. So so that is actually how reversible and equilibrium actually are intertwined. So anyway, this, but still I say maintain that if it is exactly PT, then it is equilibrium no process. That means by making no process, to make it reversible process, it is P minus dP. Achha, equilibrium, when it is equilibrium, exactly perfect equilibrium, G of this is G of that. But you slightly violate, infinitesimally violate, making P minus dP and T remaining there. Then also this equilibrium, this relation is still maintained. Reversible process still also maintaining the equilibrium because pressure has changed only P minus dP and temperature T. So this, okay, but the process is there. dn moles changes, dn moles will change, but maintaining the free energy of GH2O, liquid, GH2 vapor, as I have said, maintaining this. But anyway, complete this will be obtained. Delta GPT will be delta GPT will be obtained by integration of equation 3. By integrate this, by integration, by integration. No, this is again, this happens when I talk too much, too long. By integration of, by integration of equation 3. What you get out of that? That's for finite change integration dgpt is what you get. What you get, this dgpt is what? Is what if you integrate this delta g prime integration dg, I'm writing delta g pt is integration of dg pt dg, dg prime I'm getting, delta g prime, no problem, same. Okay, if you understand this, no problem. Integration dg prime pt is what? Delta g is what? Right? Integrate this remains unchanged, and integration of dn. So this comes out integration is GH2 vapor, which is unchanged, outside, minus GH2 liquid, unchanged, they together, outside, and integration of dn I'm writing. Integration of dn is what? Nothing but like this, GH2 liquid, GH2 vapor, right here is GH2 vapor minus GH2 liquid, and what you write here, integration dn is delta. That is your delta g prime dt. Okay, this is this delta. Oh, by the way, sorry, is delta n. Is very good, delta n, very good. But what it is? See, this is what? This delta n for under the same condition of equilibrium inside reversible condition. This, what is that? What is that? See, this condition of equilibrium is this same, minus, again minus. So 0 is very important statement, is by no means, okay, by no means actually ignore this, is 0, or okay, or this actually forget to note this. Okay, is 0. See, delta g. So right here in short, delta g prime, once more, pt is also 0. So this dgpt is 0, delta g. Reversible process. Infinitesimal change, finite change, no problem. Thank you very much. With these words, this is actually only a small item left here in this category, reversible process, that I will cover next day, and I will pick up other examples, 2 more examples for reversible process. So it will take actually some time for reversible process, with the reversible process. Thank you very much for your attention, for your cooperation, and for your sincerity, interest. Thank you very much. So we will call it a day to now, and we will meet you next class. Thank you very much. Bye.